The magic button, Jeff. Looks like you did. So, welcome everybody to the University Lowbrow Astronomers June meeting. Just as a reminder, we are going to upload, or we are recording currently. We'll upload this recording to YouTube later on. So we have to be on our best behavior, of course. Also, as Jeff was pointing out just moments ago, we're really building quite a library on YouTube of really useful talks. So it's something to consider. If somebody asks you about a particular subject, we might actually have a presentation there about it. So, as usual, go ahead, Jeff.
I would say I'll try to get out the URL for. We have actually a playlist and a search term. You can search for Lowbrow and you usually find it in YouTube, but we do have a specific playlist. I'll see if I can't find that URL and get it out to the group. Because there's a lot of material there now. Even some non-meeting talks too, so it's fun.
And they're all better than what's on TV. So.
Yes.
Yeah. So as traditional, we're going to hear from our guest speaker tonight first, and then we'll have some officer reports and updates after that. And I'm really excited about tonight because this is the return of, I think, one of the more entertaining speakers we've had in quite some time, and that is Dr. Zachary Constan from our friends up at Michigan State University. He has a great sense of humor, and yet as we go along, you're going to learn a lot from him and enjoy it all the way. He happens to be the outreach coordinator and has been for over 15 years for the National Superconducting Cyclotron Laboratory. In this case, the rare isotope beam. Help me there, Zach. What's the name of it again?
Then the new name is the Facility for Rare Isotope Beams, or FRIB.
Oh, cool, because you got the new name anyway. Thank you.
There you
go. Anyway, it's on the campus of Michigan State University. And basically, as the name would imply, they use rare isotope beams to produce the particles and nuclei that they study. In partnership with volunteer faculty members, MSU students, public residents, and teachers around the region, he has developed and conducted facility tours, summer programs for teachers and students, workshops and curricula for K through 12 students and their teachers, presentations for science festivals, and many other activities. Their facility has about 4,000 visitors a year. Last year, Zach won the ARIS Impact Award, and that stands for Advancing Research Impact in Society, for engaging the public, generating enthusiasm and learning among young people for scientific careers, and building innovative collaborations that cross disciplines to illustrate and translate the power of research in physics and other areas to the public. And tonight we're honored to have Zach back with us for a presentation titled almost 14 billion years of nuclei. Although MSU and U of M are friends in science, we are hardcore rivals in sports, and Zach is not afraid to have some fun with that. So we'll see how this goes. Please welcome Dr. Zachary Constan, also known as Dr. Z.
Thanks.
You got the floor.
Charles, I appreciate it. Thanks for that great introduction. This is now I can say without pretension that I'm award-winning outreach coordinator.
Congratulations.
It's nice. I love talking to audiences about what we do in the laboratory at Michigan State. So thanks for having me back for this. I remember coming to see you. It was probably 2019, maybe 2018. But you're a great audience. I can tell you that right now. We had a lot of fun, and it was great. It was very friendly to go visit this campus of U of M. I wasn't sure, but you made it that way. So tonight I'm going to talk about a little bit of different stuff. Of course, like you said, 14 billion years of nuclei, almost. Essentially, we're going to talk about what we've learned so far about the origins of elements in our universe. And then towards the end, we'll get into how the current laboratory, the Facility for Rare Isotope Beams, FRIB, is helping to advance that knowledge and discovering new things. Because it is, if you've been watching the news, it's been in the news because we just opened it. Like, we've been running cyclotrons for a long time, but we just opened this new lab a month ago. So it's kind of an exciting time to be talking about it. So your timing is really exquisite, really truly. So I'm going to get started. If I will try to watch the chat. We'll see how well I do that. But if you have questions during, you can ask, or you can wait to the end, and that's fine too. And all right, so let's get started. So I'm representing, of course, both the Facility for Rare Isotope Beams, FRIB, and also GINA, the Joint Institute for Nuclear Astrophysics. That is it is joint, obviously, between Michigan State University and Notre Dame, another fan favorite, I'm sure, in your crowd, and University of Washington and Arizona State University. Just a lot of nuclear scientists, astrophysicists, astronomers working together to solve various problems. And I'll tell you a little bit more about them before we get done. But this talk is all about astrophysics, which is kind of in your lane, which is why I wanted to tell you about it. I like to start with this. How do we know all these things? I make a lot of statements that are pretty blanket. I'm like, oh, we know this and this and this. And in general, I try to include evidence for that. But like, it's important to realize, how we've learned what we've learned. And this is probably something you've heard of before, but I just like making the point. In common language, we use the word theory as guess. But in science, what it means is this is a good explanation that we have, and it fits observations that we have. So it is an explanation for why things are the way they are. And there are things called laws and hypotheses. They're a little bit different, but we use a lot of theories in science, and that doesn't mean it's a guess. It means this is an explanation that we have, and it's supported. And of course, like I said, observable, testable, and repeatable facts. People are always testing theories, which is great. And to this day, people are still testing like the theory of relativity and that kind of stuff. But it's been verified over and over and over again. But it keeps making new and interesting predictions. And so that's the kind of thing we need to do. So these theories get tested and they come through. And there are more than one way to kind of support that theory, which is also important. And so when you get things like the theory of evolution and relativity and that kind of stuff, they're really long lasting because they just keep accurately explaining what we're looking at, which is great. It's important to note theories, it's not about whether you believe in things or not. It is about whether you accept the evidence and whether or not it supports the theory in question. That's what we're dealing with. So we're going to talk about a lot of things that are pretty far-fetched that but we do have evidence for, and the theories are pretty sound. So what are we talking about? 14 billion years of nuclei. Well, we've got our solar system here. It's not quite that old. Our solar system, of course, is less than 5 billion years old, but it is made of matter. So are you, so am I. Matter everywhere. And it had to come from somewhere, right? It didn't just appear. There's an origin for all this stuff. Plus, there's a lot of other questions that we have. This is science for you. We got a lot of questions, and we're curious. We're trying to figure out all these things. So that's what we're going to be talking about today. But the core, where did it come from? And our laboratory in the middle of Michigan State University is helping to answer that question. FRIB. I know it looks like FRIB. I know it is pronounced FRIB. I work there. You have to trust me, okay? But at the Facility for Rare Isotope Beams in the middle of campus. If you've ever been on campus, we're about a block away from the dairy store, which is the finest ice cream you'll ever have. We can talk about sports, and I don't really care all that much, but our ice cream is exceptional. It really, truly is. But this building in the middle of campus is where we study, of course, the nucleus of the atom, right? So we're all into the nuclear science. That's our business. Of course, there are people out there, atomic physicists, there are molecular people, there are people who are doing high energy, so the tiniest particles, quarks, gluons. Our scale, what we're interested in is the nucleus, and that's our business. So we're going to be talking about nuclear astrophysics. So, of course, atoms, which have nuclei in them, can be one of many different elements. And you've seen the periodic table before, probably, right? The thing is, every element on here has a different number. Those numbers are the different numbers of protons. That's what determines an element, how many protons. So 6 is carbon, 8 is oxygen, et cetera, et cetera. And like I said, all these different elements had to have an origin. They came from somewhere. Some of them did not exist in nature. Some of them you could not find anywhere in nature, but we made them, right? So there are, in fact, some artificial elements. I mean, it's possible that something somewhere in the universe is making these, but like we haven't observed them anywhere except when we made them ourselves. And now we're up to element 118. You might have heard of that, Ogana-san. But yeah, point is, there's a lot of elements. We can explain some of these pretty simply because we've made them ourselves, but that does leave a lot of elements, 92 naturally occurring elements that we don't necessarily know where they came from. And it gets better because not only are there a lot of them, but they have incredibly broad range of abundance is what it's called. So if you look at this shows you atomic number. So this is just different elements. And then this is relative abundance, and it's a logarithmic scale. So basically a small difference on this is a big difference. So this is a factor of 100, each of these ticks on here. So as you can see, there is a lot of hydrogen and helium. There's very little lithium, beryllium, and boron. Then you go back up, and then there's less over here. And you can also see there's this kind of interesting seesaw pattern. We go up and down and up and down. You know, like, so not only do we need to know where all these elements come from, but like, why would it be like this? Why would there be lots of this and not a lot of that? And why is this more than that? And it's very strange. And of course, why does it drop off like crazy? Right after iron, the number of nuclei drops off really, really hard. And so again, these are questions about our universe that we want to answer, and we're trying. And I'm going to show you the things that we've learned so far. Of course, we're going to cover the entire history. So we're talking about 14 billion years, 13.8, it's close. And this just shows you the beginning of time to now. Today, this is how the universe looks, obviously. But of course, at the beginning, it was a Big Bang. And shortly after the Big Bang, and this is suggesting about a microsecond to about 3 minutes, is when the first nuclei were made. And this is what we know based on a couple things. Number one, simulations of how particles basically come into existence in a high energy environment. And of course, the Big Bang was the highest energy environment you can imagine. We can now reproduce that environment with some of the biggest accelerators in the world. Of course, you might have heard of the Large Hadron Collider at CERN in Switzerland. Another one that's really big, is really interesting, is the Relativistic Heavy Ion Collider, RHIC, on Long Island. It's at Brookhaven National Laboratory. But basically, based on nuclear theory and measurements we've been able to make, this was the suggestion based on the Big Bang theory that as the universe began to cool from the Big Bang, within the first 3 minutes, out of that energy of the Big Bang, matter could form. You might be aware, E equals mc squared. Energy and matter are the same thing. They really are. And you can go back and forth. So from the energy of the Big Bang, matter formed. It was the simplest matter, like simple protons and neutrons. But based on the Big Bang theory, the prediction was you'd get a lot more protons than neutrons. Basically, for every 2 neutrons that were made coming out of that energy, there would be about 14 protons. So this is a prediction of the Big Bang theory, right? Not the TV show, which is funny, and I'll give you that, but like I need to make that distinction sometimes. So this is the prediction, and of course, so this, then you should say, okay, well then if there's 2 neutrons, neutrons do not stay free for very long. If there are protons around, they're going to combine and make a nucleus. So what this suggests is you're going to get a helium-4 and 12 hydrogens. That's going to be the relative abundance of those 2 elements in the early universe, suggesting that the mass of the early universe, this was the only 2 elements that could form, the lightest, simplest elements to make. So suggesting that the early universe should be about 3/4 hydrogen by mass and 1/4 helium by mass. And if you look at the oldest gases that we can find, and there are ways to find that, and you look at the oldest stars, of course, it also works. This is exactly what you find. That is the percentage of each that you would expect to see. So it worked out. The Big Bang theory makes a great prediction based on the observations we're making. Of course, the way you can tell what elements are out there is called spectroscopy, meaning that every specific element actually gives off unique colors, especially if it's in a gas. So what I've got here is a picture of a nebula. And if you look out in space and you see a pink nebula, it's hydrogen, because the combination of colors that are emitted specifically by hydrogen, the eye perceives it as pink. There you go. Of course, you might have seen, neon. Neon gives off a pretty obvious color. It's pretty recognizable. And this is different for all sorts of different elements. If you've ever seen element lamps of different elements, you get different colors, and that's great. But so based on the specific colors of light you get from a gas or a star or whatever, you can actually use that information. It matches up with specifically electron energy transitions. We do not need to get into the physics, but bottom line, quantum mechanics makes it necessary for each element to have a unique set of colors. And so you can actually tell, and you can tell what elements there are. And of course, by the amount of light in each of these groups. So if there's a lot more hydrogen than helium, you would expect to find quite a bit more light, hydrogen colors specifically, than the helium colors. And again, that's how we can tell the relative abundance of those two. So ladies, it's unique for every element. So it is kind of like a fingerprint. It is readily identifiable, which is great. And of course, people often ask about the Big Bang. How do you know? How do you know? You weren't there. It's 14 billion years ago. It's ridiculous. One of the predictions of the Big Bang essentially is that the entire universe was contained within the Big Bang, which means that where we are now, we are still inside of it. Everything that you see was inside of it. And so no matter what direction you look, essentially, if you look far enough away, which means back in time enough, you're looking back to, early universe. In the universe, of course, if there was a Big Bang, it was all very uniform, relatively. Everything was kind of together and it was all mixed up. And so we put up a satellite called WMAP, Wilkinson Microwave Anisotropy Probe. Wow, that's a mouthful. But what's great about this particular satellite is when it looked in every direction in the universe looked pretty much the same in every direction. We got light, very old light from not quite the Big Bang. It was 380,000 years after. The reason that is because that's the time when atoms actually formed. Before it was kind of free charged particles floating around, and that made it very, light basically couldn't travel a long distance. The universe was opaque to light until atoms basically combined, and that kind of got the charged particles out of the way, so light could travel freely. But as of 380,000 years ago, you see that light. We call this sort of echoes of the Big Bang. You can see it in every direction. So that's one way we know that's how it was. So I've now explained the origins. Hopefully, there's more evidence, obviously, but I can only go so far. Hydrogen, helium, Big Bang made them. Great. We only have 90 more to go. What time is it? Okay, so moving on. Of course, right after the Big Bang, there was an awful lot of hydrogen and helium. Today, still pretty much a lot. But if you compare the abundance of elements in our solar system to the oldest gases and stars we can measure, the oldest gases and stars have hydrogen, helium, and almost nothing else. Whereas today, our solar system has still a lot of hydrogen, go back, and a little more helium now than it used to, and more of everything else. You're astronomers, so you probably have heard, for some reason, astronomers refer to every element heavier than helium as a metal. Wow. I mean, if I was a chemist, I'd be really offended, but I'm a physicist, so I don't really care. But in the end, we're talking about all the elements heavier than helium. But of course, these all have come into being since the Big Bang. The Big Bang really only made hydrogen and helium, maybe a little lithium, that's kind of what this stuff is down here. But like all these other things have been made since. So something else is happening with nuclei in the universe. So we're trying to figure this out. And what's making it? Well, the way to make new nuclei is to have nuclei react with each other, nuclear reactions. And there are different ways for that to happen. Okay. particles can capture on the nucleus. So here's a neutron comes flying in, sticks on an iron and changes the nucleus. Actually can change it to something from something stable to something radioactive. Fine. There can be a nucleus that already is radioactive and it decays. And so essentially part of it changes and it shoots out particles and light and who knows what. Then there's fusion, where whole nuclei get stuck together and make something heavier. So if new nuclei are being made, new elements beyond helium, that means nuclear reactions are happening. That's what's making them. So where are the reactions occurring is the real question. Well, we are currently in the age of stars. Stars, of course, are just giant balls of gas, really, really hot. And they're so hot, of course, that the nuclei inside are moving so fast that they can run into each other and reactions are occurring. We call this stellar nucleosynthesis, meaning the creation of new elements in a star. There you go. So let's talk about the sun, because it's just a good example. Our sun, like other stars, it shines, and how it shines, of course, is important. I used to teach astronomy, and I really enjoyed telling people, well, let's just imagine it's just a giant ball of coal and we're burning it. You can tell how long it would burn based on how much energy is being released. If I've got a kilogram of coal and you burn it, you can tell, this is how I get this much energy. So then you say, okay, so if I'm basically shooting out this much energy per second, it's called luminosity. How long will it last? Well, you take the amount of fuel you have and you divide by how fast are you using that fuel. That bottom line. Of course, the sun is releasing a ridiculous amount of energy. It's incredible. Okay, and the mass of the sun is high. It's very, very high, but it is burning very, very, very fast. So it's important to note it's not just on fire, even though it looks like it's on fire, right? Because if you were burning coal, for instance, or wood or something, at the rate that the sun is releasing energy, to burn through the amount of mass that the sun is, even if it was just a giant ball of coal, it would take 10,000 years. We know from a lot of things that the Earth is 4.7 billion years old, that the solar system is probably about the same age. Therefore, the sun should have burnt out a long time ago, and that's clearly not right. But of course, nuclear power, you can produce a ridiculous amount of energy per nuclear reaction. Of course, it's a tiny amount compared to us, but like there's so many nuclei in there. And again, E equals MC squared. You're converting, literally directly converting some of the mass of these nuclei into energy. And if you use that kind of calculation, you're like, okay, based on the mass of the sun, how long could it possibly burn? You come out to more like 10 billion years. So thankfully, right, the star will be around much longer to help us out, which is great. Of course, now this is important. Fusion does happen in stars, and there's got to be a good reason. Of course, what's going on is all these charged particles, nuclei, protons in this case, because it's hydrogen, normally will not get anywhere near each other because like charges repel. And the fact that they're both positively charged means they don't want to get close. But a star is so hot, high temperature just is a measure of how fast the particles are moving. So it's so hot in the sun that those particles do in fact, get close and run into each other. And when things are very, very close together, while the electromagnetic force is what pushes them apart, the nuclear strong force, which is strong, it's right there in the name, it's 137 times stronger than the electromagnetic force. So if you get close enough, that's the thing, it only works at very, very short distances. I'm talking 10 to the minus 15 meters. But if you get things close enough, then the nuclear strong force completely overpowers the electromagnetic repulsion. So it is possible, if you do this kind of fusion, you get these nuclei close together, they will stick, they'll do some decays and things. So what ends up happening is you start with 4 protons, and through a series of reactions, you can eventually get a helium-4. So our sun, this is normal fusion in a star. Our sun is taking protons, hydrogen, turning them into helium. They're also releasing positrons. You don't need to know, but it's anti-electrons. Have you ever heard of antimatter? That's what you're getting. And also releases neutrinos. Great. So here's the important thing. again, the sun is producing a lot of energy. Why? Because the mass of those 4 protons is less than the mass of all the particles that come out of that reaction. The fusion reaction, you end up with less mass than you started with. Where did the mass go? Energy, right? You've lost 0.7% of the mass, and because E equals mc squared, the mass times the speed of light squared, a tiny amount of mass creates a really large amount of energy. So that's how it works. You also get neutrinos and things. And I promised I'd tell you this is how we know things. Well, you can't observe the center of the sun where fusion is actually occurring, and you definitely don't want to go there. We are detecting neutrinos that are released from the sun, and they are a great example, evidence that fusion reactions are occurring in the stellar environment, which is great. In fact, they are direct messengers from the core. The light generated in the sun actually takes about 1 million years to get to the surface because the sun, there's a lot of things in the way. But neutrinos, it is incredibly difficult to stop a neutrino. So they travel straight out of the sun and they reach us within 8 minutes. So yeah, that's a little faster than 1 million years, but that's a great piece of evidence for us that fusion is going on. So that's something that stars can do, fusing hydrogen into helium. The thing is, of course, the fusion is occurring in the core, at the center of the star. People often look at the sun, they're like, oh, fusion is happening everywhere. Well, the hottest, densest part of the star is the core, and that's really where the fusion can happen. And eventually the hydrogen in that, okay, so this is about balance. The lifetime of a star is determined essentially by the balance of the gravity pulling all the gases together in the star versus the pressure, which is generated by high temperature and energy of the fusion in the center. So as long as it's doing this fusion, it's pushing out even while the gravity is pushing in. And so it's at equilibrium, it balances, and so the star doesn't collapse. But of course, eventually the amount of hydrogen available for fusion in the core of the star, in our sun, will run out. And at that point, the pressure will go down in the core and the gravity will tend to compress the star. Well, as it compresses, it increases the pressure and temperature at the core. Eventually, the core of our sun will get hot enough that helium can begin to fuse. You take helium nuclei and put them together. They need a higher temperature to do that. And hydrogen around that center, hydrogen that previously wasn't hot enough to fuse, now is. So essentially, the collapse of the sun at some point will induce new fusion to occur, 2 different kinds of fusion, and that will increase the pressure so much that the star will inflate to much larger size. When our sun finally goes red giant, that's what it's called, our sun will swallow Mercury, Venus, and the Earth. That's how big it will get, or at least that's the prediction. It's a pretty good guess, though. But of course, it's doing new fusion in the core. And this new fusion, helium, essentially is just, I'm taking 3 helium-4s together and jamming together. The reason helium didn't fuse before is because it's harder to stick them together. Getting 2 protons to get close takes a lot of work. Getting 2 sets of 2 protons, their repulsion is even higher. And so it's more difficult to get them close enough to fuse. So that's why you need the higher temperature to get there. Now, this is a really important point. If you just fuse 2 helium-4s together, you get beryllium-8. Beryllium-8 is what we call an unbound nucleus. And when I say it decays immediately, I mean less than 1/millionth of a billionth of a second. Basically, you make a beryllium-8 and pretty much immediately, it comes apart again into 2 helium-4s. So this is something that Fred Hoyle, who's a famous astronomer, made a prediction of. He said, well, maybe it's 3 alpha particles, helium-4s, all fusing at the same time. Well, if that happens, you get carbon-12, which of course is the basis of all life on Earth. So thanks to stars doing this kind of reaction specifically, we have life, which is great. That's where it comes from, carbon-12. So now we finally made something new, right? We had hydrogen and helium before, the Big Bang made it, but now we've got something entirely new. And really, the stars, that are really, really massive, when they undergo these collapses after running out of gas, essentially, they'll get hot enough to fuse carbon and helium into oxygen, and oxygen and helium into neon. This is neon helium over and over again because that's kind of what's available in large part. So you can, as long as the temperature keeps going up, it makes it easier to fuse heavier and heavier nuclei. Eventually, if you have a really, really massive star in this red giant phase, you can get a lot of things fusing. Low mass stars like our sun, helium and carbon is the farthest it's ever going to go. It's not massive enough to ever get hot enough to fuse heavier stuff. But we talk about a high mass star like Betelgeuse or Rigel or that kind of thing. It's basically going to have enough high enough temperature at the core to actually fuse things all the way up to iron. And you get kind of this onion layering effect at the core where all that fusion is going on. So here you go. We can fill in a little bit more of the chart now, the periodic table. Essentially, fusion in stars, like our sun, but probably more heavier stars, can result in these elements. Based on our understanding of the nuclear reactions going on, these are the elements made up to iron, and iron is as far as you go. So we're starting to fill in. It's getting better, but there's still a lot left to go. The reason iron is the farthest you can go is because the reason a star, exists, the reason it shines is because it's producing energy. Fusion produces energy because when you take nuclei, light nuclei, and you jam them together, you end up with less mass, which then means that energy came out, right? New energy was produced by that lost mass. Well, if you fuse hydrogen to helium, you get some energy. If you fuse helium to carbon to oxygen, you're getting energy. You get to iron, it's energy. But if you fuse iron into something heavier, see on this chart, this is the amount of mass per particle. If I try to fuse iron into something else, it's got more mass per particle than it did before. So instead of losing mass to produce light, I'm gaining mass. You can't fuse iron into something heavier. It just won't work. You have to put energy into the system to make it work, and it's not going to. Of course, you go the other way. You start with something really heavy and fission, split the element, split the nucleus. Then you can get energy too. So anyway, point is, iron is the stop sign. You fuse with a really massive star up to iron, and that's as far as you're ever going to get. Of course, that's why you look at this and you say, oh, okay, iron, there's a lot of iron. And that really suggests that, fusion is what's creating a lot of these elements, because iron is the end point. It's going to be, of course, like I said, it's the lowest mass per particle. So is energetically favorable for you to end up making iron. And the fact that the nuclei drop off after iron means, of course, is one example is stars can't make it. Stars can't fuse iron into something heavier. So you're going to get less stuff after iron. It's true. I did point out that a lot of these fusions were helium capture. That's not the only kind of thing, but helium capture is very common. Of course, helium has 2 protons. Well, if you have carbon and you add 2, you get oxygen. You add 2, you get neon. 2. So you see the even numbers on here are more abundant. There are more of them than the odd numbers. And that is an effect of the fact that you've got helium fusing onto these nuclei. So, what we know about nuclear reactions is helping us to understand and explain why we have this weird pattern in our abundance in our universe. Now, of course, there's a lot less because stars aren't making them with fusion, but they do exist. So, the real question is, why do we have them at all? Like, what could possibly be making these? I'm not going to leave you hanging. There's actually some idea. Okay. So the thing is, like I said, you try to fuse iron into something heavier, you can't. And one of the reasons in the end is because you've got a lot of protons, and it's just really difficult to get anything else to stick. Things repel. But neutrons are neutral. If you have neutrons hanging around, it would not be that hard to get them to attach to a nucleus. Great. Here's the problem. If you have neutrons around just by themselves, they are radioactive by themselves. A neutron alone outside of a nucleus with protons has a half-life of 10 minutes. So in our universe, you don't see loose neutrons. They just aren't around. So like, how could this ever happen? Like, it'd be great if we could, it's possible for neutrons to attach to an iron, but they aren't available. Well, they might be under certain circumstances, right? Even if they're short-lived, maybe there's somewhere that's making neutrons available on a regular basis. And one possible place is a red giant or supergiant. So here, again, I just mentioned Betelgeuse. Here you go, the armpit of Orion, right? And it's an incredibly ridiculously large red supergiant. It is believed that there are nuclear reactions that can occur in a red giant or supergiant that would produce on a regular basis neutrons that could attach to an iron. And if this happened, right, if there are neutrons available, then the iron that the star has made, or maybe some other, heavy element, whatever, maybe that could add a few neutrons onto it. Okay. Neutron capture is what we call it. Well, if you add neutrons onto a nucleus, you're eventually going to get something that's radioactive. It is unstable because it has too many neutrons, essentially. And it basically, the reason it's unstable is it has too much energy, excess energy. Things in our universe don't like extra energy. They want to get rid of it. And a radioactive nucleus does so by decaying, which means, in this case, the neutron turns to a proton, releases an electron and an anti-neutrino. Bottom line stuff comes out. But what's important here is the neutron turned into a proton. So instead of iron, now you have cobalt. You have one element higher than iron because you added neutrons, which don't change the element. Eventually they decay and become protons, which do. Okay, so you can get a heavier element through neutron captures, which are a lot easier to do than fusion, as long as the neutrons are available. Now, of course, that new stable nucleus, cobalt 59, maybe that catches the neutron, right? And this could go on. So in a red giant, they call this the S process, slow neutron capture. And one of the ways we know that's going on is that we can look at, again, the spectrum, the light from a red giant. And here we have specific lines that tell you there is a technetium nucleus in there. So that's the element that's named technetium, element 43. And it's my favorite element because of all the, elements exist in our universe because they've been made. And, you look around on Earth and you find all these elements. But element 43, which is really in the middle of all the elements that exist naturally, technetium is pretty short-lived, short being 4 million years. Well, here's the thing. The Earth is, over 4 billion years old. If the Earth formed and had a ton of technetium on it, it would have all decayed by now. But this star, which is billions of years old, has technetium in it. And that means there are radioactive, there are nuclear reactions going on. And it's not fusion because fusion can't get as high as element 43. It stops at 26, iron. So something is making heavier elements. And so this is why we think a red giant, this particular one, and any one, might have neutrons available to do this neutron capture process and make heavier elements. So based on the predictions, based on what we know of red giants and possible neutron captures, we think it explains these elements. Maybe not fully, maybe not everything, maybe not all of that element in our universe, but explains a lot of things about it. So, it exists. Good job, S process. But this is the thing. Every time you make a prediction and you look at your periodic table, you can see there's holes, there's gaps. So there's got to be something else making the other stuff because it does exist. It's coming from somewhere. So we talked about the S process, slow neutron capture process that would occur in red giants. Of course, red giants, the big ones, like Betelgeuse, at the end of their life will go supernova. They will explode. And now why they explode, that's something that's still being worked on. But like we've observed, the remnants of explosions. of course, also know that you'll end up with a core that was either a neutron star or it's right there in the name. And if for some reason two neutron stars merge, when that could happen in a binary system where there are two stars orbiting each other, maybe towards the end of their lives, they both die, they both make a neutron star. And over time, and it could take a long time, they will come together and merge and literally collide. There's a lot of energy in that environment, a lot of loose neutrons available. I mean, it's like a big nucleus, really. That's what a neutron star kind of is, a giant nucleus. Well, in a neutron star merger, if you've got maybe some stable elements, hanging around, then neutrons could attach, and then you make something radioactive. But there's so many neutrons around, a new one attaches. Even though that's radioactive, a new one attaches. I mean, essentially, neutrons could be captured onto a nucleus so fast that you'll make something, really radioactive, incredibly short-lived, which will decay. But then that's probably going to be radioactive, and that's going to decay, and we're going to add more neutrons, and it's going to happen so fast. We call it the R process, rapid neutron capture. They're so good with these names. I mean, you've been in astronomy, you probably know. We're all about names. R process, S process. It's just how fast are you catching your neutrons? And we think a neutron star merger, you capture them so fast, you make such unstable nuclei that you could end up making very different elements, not the same ones as the S process made. What I have here is a short little animation. It is a simulation of when the R process occurs. Neutron stars are one place that it could occur. We also think maybe in a supernova, you can also get some R process, rapid neutron captures. But the idea here is I'm going to let the R process happen, meaning a lot of neutrons flying around really fast because it's high energy. And I'm going to start with some iron. So you can see the little red box there. I'm going to have some iron, and I'm going to expose it to all these neutrons. And basically, I'm going to run this simulation, and it'll show you what could be made with those neutrons attaching to iron. A couple of things you need to know. If it's red, that means there's a lot of them. Blue is very few. This is the current temperature in the R process area. This is 1.5 gigakelvin. That's pretty hot. Just trust me on that. And then the time is the time after this reaction has started, whether the supernova or the neutron star merger, something violent happened, and we're starting the R process. Within 1 second, you make all these different isotopes. These are all very rare and radioactive. I should have also added the black squares that you see here are the stable and common isotopes. So all this stuff over here are not only radioactive, they're really radioactive. This is way out in the fringes. These nuclei just do not exist ever naturally on Earth. But this incredibly hot, dense, violent environment can make all these different isotopes. But they will decay. And when they do, those neutrons are going to convert essentially to protons, and they're going to move up and to the left. Eventually they'll land, become stable isotopes. They will keep changing, releasing extra energy until they become the stable isotopes. And these are the elements we know and love: gold, lead, silver, uranium. You can see that this particular model has predicted you get a lot of these and a lot of these and maybe not so many of these. So when you do these kinds of calculations, it's nice to be able to compare what you've learned. This is a theory. Let's compare what we predict to exist with what the universe actually has. So are we right, or what are we missing in the physics? That kind of stuff. So this is a simulation, of course, but based on the simulations we've done and the observations we made in elements after a supernova, after a neutron star merger, you might be aware of the neutron star merger in 2017 that was actually observed by gravitational waves. It's a long story, but we've actually seen the aftermath of a real neutron star merger, and we know it was. So essentially, we think that's how we get the elements beyond iron, based on what we know. Neutron capture, that's what's got to happen. And it could be slow neutron capture, S process, or rapid neutron capture, R process. That fills in almost everything. It really does. That doesn't mean they explain everything. There's even the R process and S process don't predict all of the kinds of all the nuclei that we do observe. And so there might be other ones. P process, proton captures. I process, intermediate neutron capture. So it's not fast, but it's not slow. And where could that happen? Well, the people are working on it. So there's a lot of other processes. And then of course, there's these lightest nuclei. We think they're made by cosmic rays sputtering. It's a long story, but eventually we have enough candidates for things that could actually make these to fill in the entire periodic table. So 14 billion years, we've made all these elements. And it's because stars, of course, are forming and dying. They're exploding. They're forming new stars. There's a lot of fusion going on. There's neutron star mergers. But it's because that stars live and die that they're enriching the universe with heavier elements beyond hydrogen and helium. That's what stars do for us. And of course, GINA, the Joint Institute for Nuclear Astrophysics. What we do is essentially combine what astronomers observe, how's the universe really, with theory, with predictions of, okay, so I think we can explain what we're seeing here, but with this kind of process, the rapid neutron capture or whatever. And then of course, a laboratory like ours at Michigan State exists to run experiments and try to see, could those reactions work in a stellar environment? And these three working together are helping us really understand where this is coming from. Yes, here's an important question. Can you explain why stable elements tend to have more neutrons than protons? Protons are positively charged and they repel each other. And so they tend to increase the amount of energy in the nucleus. And like I said, the universe wants to have lower energy stuff. Essentially, by putting neutrons in the way, they call it having the neutrons mediate the strong force. So I've got protons on either side. Now, not literally, but having neutrons in the mix lowers that energy. Of course, there is a limit, but it's true. You tend to have more neutrons than protons. The stable stuff, when you get down to the lightest elements, is about the same number of protons and neutrons. And for whatever reason, with the rules surrounding the strong nuclear force, that happens to be the lowest energy. But when you get more and more protons, you tend to need even more neutrons to make a stable nucleus. Okay, so finally we get to what we actually have at MSU. What we've had are cyclotrons, and people know us as the cyclotron, and people would call us that. And maybe you've heard our laboratory referred to as the cyclotron. And we were using cyclotrons since 1965 until a couple years ago. We've been doing really good work for decades, over 50 years. And so our lab, was using those cyclotrons to make rare isotopes of the types that maybe are existent stars or neutron star mergers or whatever. And we were so good at it, we were top 3 in the world. Top 3 in the world for making and studying rare isotopes. Super duper, right? That's pretty great. It is clearly not good enough, as you probably know. So we've always been upgrading. I mean, like ever since the first laboratory, 1964, we've always been upgrading and improving, because that's science for you. And we just finished the biggest upgrade we've ever made. And again, we've changed our name. We're now the Facility for Rare Isotope Beams, FRIB. Why? Because we're not using cyclotrons at all anymore. We shut them down. We don't need them anymore. Because with $730 million from the US Department of Energy, also the state of Michigan, also MSU, with that money, we replaced the cyclotrons with a 400-yard long linear accelerator, 32 feet underground. Essentially, nuclei start at one end, we accelerate down a tunnel, they go in pretty fast, we turn them around, we accelerate them again, they're going faster, and we accelerate them a third time, and now they're going half the speed of light. That is 4 times around the Earth per second, which is just not bad, right? Not bad. So essentially, the way we make rare isotopes is really straightforward. If you know anything about physics, we break stuff. Like that's our business. We smash things. So we take normal nuclei. So I've just got an example here. Right? This is protons and neutrons, clearly a nucleus. This is a carbon-12. which is a stable common form. But if I throw it against the wall, and I'm not going to, I'd knock off some pieces, protons and neutrons. What's left behind is different. And if we knock off the right number of protons and neutrons, we can create a rare radioactive isotope, a nucleus that would not exist on Earth naturally, but we can make in our laboratory. And so this new accelerator is actually going to smash so many more nuclei per second. We expect to discover over 1,000 isotopes that no one has ever seen. In the history of humanity, we've discovered 3,000-ish isotopes. That's not bad. With our lab's cyclotrons, we discovered about 77. Not bad. The last ones we discovered, it was magnesium-40. We all got free pizza. It was a really big day at the laboratory, right? But FRIB, the new accelerator, which we just turned on last month, we're expecting to discover 1,000 new ones. That is a lot of free pizza, if you think about it. They will have to cut us off at some point. But with this new accelerator, we have access to new isotopes nobody's ever seen. We'll be able to do experiments no one on Earth can do. Now that we've turned it on, and it's been a long time coming. The last time I saw you, I talked about it. We won the project in 2008. We broke ground in 2014. And we just finished it last month. It's a long-term project. We finished it on time, by the way, and under budget. So anyway, but point is, we are now the #1 rare isotope facility in the entire world, bar none, right? MSU is known for farms and ice cream. I already mentioned that, right? But farms a lot. And yeah, sports are fine, whatever. We've got a really great college of education. They're very, very good. But we are the best rare isotope facility in the world. So basically, this is what we were able to produce, all the different isotopes we produced with the cyclotrons. And this is what we'll produce with FRIB. And we'll be able to make a lot more nuclei that we're pretty sure are made in the R process in neutron star mergers. So we'll be able to test that theory and model better than we ever have before. It's just, everything's going to be so much better, bottom line. And that's my show. Hopefully I didn't go too long, but these are other ways for you to learn about what we do at our laboratory. There is a video game, if you or somebody you know would like it. It's called Isotopes. Basically, you smash nuclei on your phone. Isn't that what you want to do? We have a museum that you can go to. There's a camps. There's a website. So look us up, basically. And that's it. There you go. You can take questions.
I'll start out. I was looking at that diagram. Maybe I didn't catch it correctly, but are you colliding two beams, or are you hitting a target with one beam?
Right. Yeah, it's a target with one beam.
Okay.
Yeah, there are other
That's what it
labs that
looked
do
like.
the opposing beams. For us, I mean, you do opposing beams if you want to get the highest possible energy. Half the speed of light is good enough for our purposes. So yeah, it's just a target, beam comes in, hits it, and then it continues on. So I've made something new that continues on and goes off to our detectors, wherever that is. Doug asked, can we produce elements beyond 118, right? There's people are always excited to discover a new element. Well, we're not really set up for that. I mean, our laboratory does this, it's called fragmentation. We're breaking nuclei down, whereas to make elements that are even heavier, you start with uranium and try to get other things to stick onto it. I mean, with the equipment we have, we could do that kind of thing, but that's not really our goal. There are other labs that do exactly that. It would be great, of course, because when you actually do make a new element, you get to name it. See, we make different isotopes, but then the element already has a name. So, I mean, if we did discover a new element, it would be spartium. Think about it. Yeah, see, I've thought about this way too much. Fantastic. Barry asked about the ratio of protons and neutrons in the early universe, according, because of the Big Bang theory, that prediction. I don't know if I can say anything else useful off the top of my head. In the end, no, this is one of the things that people are trying to figure out. the universe tends to have what we call symmetry. And so one of the biggest unanswered questions is if matter formed out of the Big Bang, shouldn't antimatter also formed out of the Big Bang? Well, yeah. So, I mean, the thing is, like, we don't run into it on a regular basis. So as far as I can tell, based on observations of the universe and things, the relative percentage of antimatter specifically compared to matter is very, we don't understand it. That's kind of getting at your question in a roundabout way. I don't think I can say anything. What we need is a particle physicist. My research was actually acoustics, which has nothing to do with any of this, but I've picked up some things. I'd be happy to look it up for you, Barry, and I'll see what I can find out. You're welcome, Jeff. My job is to, interpret a lot of very high level information for whoever the audience is. And in the end, it's something you can still appreciate, even if you don't need to know all the equations and all that stuff. It is a lot. It goes pretty deep. I already had a PhD in physics the first time I toured FRIB and saw what they were doing. And I was just like, I had no idea you could do all this stuff. I didn't understand it at all. It was very strange. But now I've been working there 16 years, right? So if you want to really understand it, come work with me for about 16 years. You'll be fine. John, I see your hands up.
Yes. Can you hear me?
Yes, no problem.
Okay, I'm retired. I worked in skilled trades at Ford Motor Company, and I years ago I copied off an astronomy picture of the day image of the periodic table with a breakdown of where the elements came from. I'm sure you're familiar with that.
Yeah,
and I had a lot of people asking with me, and these guys that I worked with, they had because they were in trade school, they had studied Newtonian physics and material science, and they were so there's some physics and chemistry there, and they started asking me about this, and I became known as a professor just because I had encountered a few of these things. I got a lot of guys to read Herman Bondi's Relativity and Common Sense, and they had geometry and algebra, so that worked out well, brought up to the Lorentz transforms. But I am certainly going to communicate them, tell them about this lecture. I think they're going to really enjoy your presentation here, and I'm glad we recorded it, because this is the best presentation that I have heard on how to really fundamentally understand the development of the periodic table. So this has been a terrific lecture, and I appreciate it immensely.
Thanks, John. On the first page, the first slide here, I had to give credit to a lot of people who are generally nuclear astrophysicists who've kind of contributed a lot of the ideas and the figures and things like that, because I'm lucky that I get to hang around with these people all the time, and I'm always poking them like, hey, so what do we know now? When I started this job, everybody was convinced that the R process occurred in supernovae. And nowadays they're like, no, we think it's more neutron star mergers, maybe a little supernovae. So it's changed a lot over the years. But thankfully I've been able to pull together all this stuff and try to communicate it in an hour. It works pretty well.
Well, that's exactly. I still was stuck on the supernovae theory. So this is great.
Yeah.
Thanks.
You're welcome, John. Doug asked if we have tours. Yes. And that's one of the reasons I like showing this page right here. You can email me, you go to that website, you can learn about tours. A big part of my job is giving tours of our laboratory to people who are interested. So, if you want to come, it's not that far up the road, it's like an hour, come up to East Lansing and I can show you around. I'm going to be honest, summer's really busy, but once we get to like August, September, things quiet down quite a bit. So if you want to come, officially, I need 10 or more people to start a new tour. Unofficially, I don't really say no to anybody. Sometimes if somebody's just like, hey, it's me and one or two people, I might be able to connect you with another tour that's already going. But I'm sure that the lowbrow astronomers could get enough people to run their own tour, almost certainly. Matthew wants to know about merging. How do we research merging stars? How long has that been doing? So we've only really had this ability to measure like ripples in space-time because of gravitational waves, and that is a long talk in and of itself, but we've only really had that ability for less than 10 years. This is one of the most exciting times in astronomy because, of course, astronomy, we've always been looking at light. And, light is a great piece of evidence and it's information that we're getting from all over the universe. But it was the only way we were really exploring the universe. With gravitational waves, we can see so far, really massive things orbiting each other in short distances. And that's usually going to be black holes or neutron stars merging. It's really only been within the last 10 years we've been able to observe this in actuality. It's at a place called LIGO, Laser Interferometer Gravitational Wave Observatory, LIGO. There's actually 3 different places that work together to combine their information and do this kind of stuff. It is crazy that they can do this now, but it works. It works, and you should look it up. LIGO, LIGO, worth checking out. Good, and yeah, I'm glad. By all means, this is good stuff to share. If you know people who are interested in this thing, it's a great way to go. Yeah, Sky and Telescope apparently has a lot of very pertinent articles. Good for them. They're paying attention out here. It is a nice public, information stream. It works really well for a lot of audiences, which is
Yeah,
good.
I was pretty surprised. It's like I'm listening to your talk, and all of a sudden it's like, hey, I just read about that, or hey, that was in last month's issue. So this is all like right burning edge stuff. That's we're reading about the glitzy level at Sky and Telescope, and this is a little more detailed. It was very interesting actually. It tied a lot of stuff together.
Yeah, that's the thing is like if you get these things in more than one location, it really helps, makes it a lot easier to understand. That's true. So good job doing your background there, Jeff. You were prepared. Well done.
I think you've really demonstrated, Zach, why you won that award.
Yeah, thanks.
Because really, that was really good stuff. That was the clearest description of this that I think I've ever seen.
Excellent. That was the goal.
With that, do we have more questions for Zach? Okay. See, you explained it so well. Nobody has questions left.
Success.
Anyway, thank you very much. Appreciate it.
You're most welcome.
So I forget, when you came down to Ann Arbor, did we give you a club T-shirt or hat or?
I don't remember. I feel like
Will he be safe
must have
wearing
been.
it back to MSU?
Yeah, they would love
Well,
that, right? I mean,
that's what I was thinking. If we gave him a shirt and he actually wore it, he apparently survived it up there. But
yeah,
but
we're not that. I mean, maybe we are a little bit. I don't know. But yeah, I mean, people walk around campus in Michigan gear and they get away with it. It's true.
yeah, actually, I've noticed that. In fact, one time I had a service call right across the street, across Grand River from campus on a cash register, and forget the reason why, but I think it was because it was where it was. My son went with me. It was getting around football season, so we dressed up in all the maize and blue that we could. And after the service call, just drove around campus just to be smart Alex, and nobody paid any attention to us whatsoever. We were so disappointed.
Oh, come on, that's too bad.
But I thought, well, that was actually very good of them to act like they completely ignored us. We weren't prepared for that. So
probably easier to ignore you. Yes.
So Charlie, regarding your question,
Yes.
Zach, when did you last talk? What year was that? Because I can look it up
up.
and see what we sent you.
I've got it here somewhere. Oh, here. I'm gonna stop.
I think it was 2019 to tell you the truth. 'Cause
That's
I had
what I'm
just
thinking.
joined. It was like springtime. It was warm and whatnot before the pandemic hit.
And it was also a warmer part of the earth thing, because
was.
remember we had to meet in a different room, and
Yeah,
it was actually in Mason Hall because our
Right.
room was flooded.
Yeah.
That's right. Yep. It
So
was
let's-
June 21st of 2019.
Wow,
June
When was it?
21st.
almost 3 years
Wow.
ago to the date.
Got all my records. I know what I'm doing.
Amazing timing.
Let's see what I have. June 2019. So
Obviously,
There it
Zach would
is.
like to offer you a club shirt or a baseball style hat, or we can go with like a restaurant gift certificate if you prefer. The hats look really nice though. Of course,
I would love a shirt. I like
yeah,
me
we
some
sent you a
regular
sh-
t-shirts.
yeah, we sent you a shirt. We sent you a size large t-shirt.
That makes sense. That
So if
makes
you want
sense.
another one, we can send you another one.
Well, I clearly
Or a
don't know where
cap.
it is. So then maybe it would be good. I promise not to lose this one. How about that? That'd be great. Thank you.
Okay.
Yes, Paul, any age is fine for tours. I always take a safety survey before we go around. So it's completely handicap accessible. We can have pregnant women, it's fine, kids of any age. They can't touch the red buttons. That's what's important.
we can't push the auto destruct button. Oh, come on.
It's the worst.
We had actually talked about doing a tour up there before. I think we should rediscuss that and see if we can actually pull it off this time. So it does sound like fun.
Yeah,
So again,
I'd go.
much appreciated, Zach. Excellent stuff.
It was my pleasure.
So is there
you all
anything
have a-
else going on? Should we have you come back in another couple of years and get an
Yeah.
update?
There will always be something new to say. That is for sure.
Yeah.
Cool.
Bring some of the
We'll keep that.
isotopes with you.
You bet.
Yeah, there you go. Yeah, we want to see some samples.
I'm always carrying isotopes. That is for sure.
Oh, cool. We'll contact you in a couple of years, let's say then. So,
Fantastic.
or maybe even toward the end of next year, something like that. So, because you're a delightful speaker.
Thanks. You're a delightful crowd.
Okay. So, with that, what size shirt should we send you?
Oh, a large, please.
Large, got it. Okay.
I'll
Okay.
follow up with, see if I have the right address and all that.
Okay.
If it hasn't changed, I'll send it to the same place.
Yeah. No problem.
Okay.
Thanks, everybody. You have a great weekend.
Thank
You
you.
too.
you.
Thank you.
Fantastic.
Thanks for the talk.
My pleasure.
Okay, sorry about that. I turned some light on here. So on officer reports, I have a couple of things here. One is I had mentioned last meeting that I've been contacted by Westland Library regarding doing an observing type event there, which actually we've done before. And they were hoping to do something this summer, but I also stated that there wasn't really much going on this summer. And being it's in an urban setting, you really kind of hope that you got some planets to look at, since there's not a lot of other stuff you can show them. I mean, some things, yes, but so anyway, I have been in contact with Aubrey, I believe her name is there. And I explained the situation to her that to really show planets, as in Jupiter, for example, we really got to wait until at least mid to late August for it to come up so we can actually have a shot at it. And but as it turns out, she said that's actually not too late. In fact, it was kind of good, because at this point they're scheduling stuff a little later in the summer anyway. In fact, she even suggested that sometime in September, even early October would be just fine. She did propose several different dates in September. I thought for sure I'd see AATB dates in there, but actually I did not. So I'm guessing that maybe one of those would work fine. I just got that email yesterday. Hadn't had a chance to take a good look at them yet, but I will, and come up with something and let everybody know about it. And it's just a matter of coming up with some help for it. So, and as I remember right, the one, maybe even 2 times we've been there before, we actually had very good turnout for that. So
I think
Anyway.
we did an evening one, and we were there during the day for a presentation and did a solar scopes out in the yard.
did we do a solar thing there?
That's what I'm remembering.
Because I remember we did that at Cromaine Library.
I've never been there, so
Okay, well, so then it wasn't that. So, okay, maybe that's the second one I'm thinking of then, but
Yeah.
anyway, so I'm working on that and I'll have some more news on it pretty soon. I also got an email from a Chinese studies group at the U of M. And they were asking about something basically around a full moon time. But that didn't line up time-wise very well either. This is, we used to in fact do this Chinese Moon Festival event quite some time ago. It was someplace in Ann Arbor. And then
Charlie, we did that
Yeah.
in Celine with a group of people who had adopted Chinese children.
yes,
And it was quite the festival. It was very enjoyable.
yeah,
So
that was
we-
going to say there was a little gap, and then it took the form that you're speaking of, John. It was out actually at a residence, kind of between where I'm at in Saline, sort of
Yeah, we did
northwest
it
of
at
Saline.
several different sites. I remember going to Canton a couple of times to do that.
Right. What eventually happened though is we were doing this almost on an annual basis, if not annual, for a while. But then what messed it up is you might remember a few years ago, astronomy at the beach schedule got messed up because we used to always try to do that closer to new moon. And then it started to get so we could not do that. In fact, we even had at least a couple of them around full moon.
Yes.
And that was a problem because we couldn't do the Chinese festival and AATB at the same time. So it's really strange. It's the kind of conflict you don't expect to run into because it's full moon, but that's what happened. So it was really frustrating because it seems like they tried 3 or 4 years in a row at least, and every time it just did not work out right.
Well, that's
so-
what happens when science and religion tries to mix.
Yeah, there you go. And then of course COVID hit, and I think even before that I might not have heard from them for a year or two. But now another group is kind of asking for the same type of thing. But we also had the same situation. I could see maybe a chance of doing something, but it would have been the weekend before astronomy at the beach. And then my concern was, well, how much turnout are we going to get that close to astronomy at the beach since we pour so much into that? At any rate, I had some discussion though, if I also explained to her astronomy at the beach and what happened there. And she was actually very interested in that and has asked for more information. So since I have sent her a link to it, and she would also like updates as we progress. So I said, when I get them, I'll pass those on to her. So it sounds like this group might want to make a presence there because that did sound quite exciting to her. So I'm glad I threw that out there. That might help them with their thing. I don't know how they would incorporate some of the little festivities that they would be doing for sure, or maybe she's not concerned about that aspect of it, but another one I'm kind of working on. So, and then just a reminder that next month we do, unless something terrible happens, expect to be in person again. But we also hope to be back over at EMU as we had been doing for a long time. Norb said that last time I talked to him that things looked like it was a green light on his end. I don't know if we're going to get into the pizza thing and all that necessarily this time, but we'll at least, as far as I know, have the meeting over there, and Norb had something in mind that he can do for a presentation. So I plan to touch base with him, make sure we're still on track there. But again, just remember July, we'll be back over at EMU because it probably collides with Art Fair again. So if we were to stay in Ann Arbor, which is the reason we went to EMU to begin with. But then
So
we had so
we're-
much fun over there, we just continued to do it until COVID ruined it.
Charlie,
Yeah, Jim?
we are going to EMU?
Yes.
Okay,
Yeah, unless, like I say, something's happened I'm not aware of. The last I knew, Norb said it was good.
all right.
So I guess what I don't know is if we'd meet in the planetarium area at Strong Hall over at Scherzer Observatory. We'll have to work that out, but that is the plan. So I'll have more details. I think that's all I had. So I would like to move to Dave, who also is going to introduce Buddy Stark for us.
Yeah, so it was a few weeks ago, I had a chat with the new planetarium director, Buddy Stark. And it looks like we have both Buddy Stark and our old planetarium director, Matt Linke, here both.
Very cool.
Thought, Buddy, you might just briefly introduce yourself. Oh, we can't hear you.
How about now?
Yeah.
Cool. So as we mentioned, I'm the new planetarium director at the University of Michigan Museum of Natural History. I'm not sure that there's a whole lot to be said about me. I am working on my PhD in science education. Have a couple of degrees, the master's degree, bachelor's degree related to that as well. I've been in planetariums in general since 2008. I started at my undergraduate as a student operator. I've spent the last 7 years managing the planetarium at Longway, or in Flint, Longway Planetarium in Flint. Before that, I spent a year managing the planetarium at the Michigan Science Center. So this is, including my student planetarium, this is my fourth planetarium. Yeah, I don't know what else might my folks be interested in. I've done a little bit. I've been involved through Longway. I've been involved with astronomy at the beach a couple times. Other related those types of activities around the state.
So it seems like the planetarium has actually been open for a while now. So, you know, people like to visit, you know.
Yeah, we reopened to the public in October. We've been running at a limited capacity since then. So we've been more or less limiting the tickets to a little less than half. Shows are still, we're only doing Friday, Saturday, Sunday, and there's just a small block when we're doing them, but we are open to the public. It's been going very smoothly. We also have, we've been open to school groups as well, but as you can imagine, it's been sort of slow on the uptake as schools have a lot of other things on their mind at the moment.
This is John Wallbank. I'm involved with astronomy at the beach. I would be very interesting in knowing about your past involvement with astronomy at the beach.
Yeah, it's pretty, I think I had told Dave about this too. For the most part, it's been pretty sort of standard in that I rented a table a couple of times through my planetarium. One time I coded a little trivia game, brought some Xbox controllers, and as the kids walked by, they could play some astronomy trivia on a monitor that I had brought by. Mostly I was manning those tables. I did occasionally get around and sort of meander with people who had set up telescopes. I attended one planning meeting through the Michigan Science Center, and that was 8 or 9 years ago. So that, in terms of other than renting a table and just sort of being present, that was my only you know, planning portion, and it wasn't much.
Well, very good. I would like to keep in touch with you, and I'd like you to keep in touch with us. So I will facilitate that. I'll be in touch.
Yeah, that sounds great.
And it was just by coincidence, I was in the museum and did catch one of the planetarium shows this morning. So yeah, I can testify that it is open.
Gotcha. You saw one this morning?
Yeah, I walked by your office. You weren't there, but
okay. So Irene was given the show then.
Yeah.
I think it was interesting, Buddy, that you mentioned the planetarium up in Flint. I graduated from Swartz Creek High School, which is kind of the southwest corner of Flint. And they actually had an astronomy club. I don't know if, maybe you know, if they still exist. It was called the Genesee Astronomical Society.
Yeah, no,
GAS for short.
My predecessor there, Richard Walker, was involved with them. And they had a hard time keeping membership. The whole time I was there, the only active astronomy club was at Seven Ponds. So I partnered, and that's in Dryden, a little ways east of Flint. So anytime I did something, observing nights and that kind of thing, I partnered with them.
Yeah, I do remember they had the meetings there at the planetarium, and there was very few people that showed up.
Yeah.
But it was kind of cool. They even, I forget who the planetarium director was at the time, but he actually let me kind of drive that planetarium one time. He gave me some basic instruction and let me at the controls. Man, I felt like Captain Kirk. And they had an old, I think it was a Zeiss optical, purely optical machine there that was just, it was just a cool thing just to look at even when it wasn't running.
Okay, cool. Yeah, they had one of there were three, what they ran when they had an optomechanical was a Spitz B projector.
Spitz, yes.
Yep. And there were only three of those in the world. It was a pretty rare, because it was kind of a monster that you had to hang with like airline cables and things. When they took that down, they sent the parts to the only one operating, which was in Portugal, I think. I mean, there was one at an Air Force base somewhere in the southwest of the United States. There was the one in Flint, and then there was the one in another country. I forget. I think it was Portugal, but I could be wrong about that.
I know it had excellent star images.
Oh yeah, I mean, a lot of those Spitz, projectors. I mean, they were.
Yeah. It looked kind of like, it reminded me of a giant ant.
Yeah,
or
exactly.
something. It was,
Yeah.
yeah.
Actually, when I started there, one of the first things we did was we took it out of storage in the in the collections facility, and we hung it. So if you go back to Long Way now, it's hanging in the lobby. The old optomechanical is.
Cool. Well, it was nice meeting you, buddy. We'll have to make it down there and check out your facility again. And I was glad to see that you could join us too, Matt. Very cool. Anything else, Dave?
Nope.
Okay, then we'll move to Jeff.
Oh boy. Yeah, today we had a max of 29 for our minute takers there. The other thing I kind of did this month was check out our various web hosting options. And I think I'll just share the screen shortly just to show everybody what I came up with. It's a rather colorful little chart, but there we go. So basically I went through a few things. They all have promotions. There's the number of websites we can do, which since we want to move our Lowbrow site in general to that, we've also got the Young Astronomers site, and we have the objective lens feature from Amy. We thought that might be a good starter thing just to try out and kick the tires on the product. They have limits on storage, like some of them, like this one had only 50 gigabyte or 30 gigabyte. I was kind of looking, it's like, I don't want to worry about storage ever because, well, we have images and that could go up very quickly, very fast. And also, if for some reason it becomes popular and we get beyond 25,000 visits, then maybe that'll be a problem. I didn't figure that was as big a deal. But the other thing that was the domain charges, some of them were yearly. This one just gave it to you. And I don't know if it was renewed yearly or not. Some of those were a little odd, and they all kind of toss in an SSL certificate. But this option here was kind of the one I was shooting for. I can talk offline with the officers on, exactly, which one they go to, but this is kind of the one I was favoring. So of course they have a low promotional price, all of them do, but the monthly here was very reasonable for all the services that you're getting. So that's kind of where I'm at now. And I wanted to talk with the officers offline to, kind of finalize things and then move forward with that. But I think because Amy's thing will be relatively easy to do initially, we might start with that, get a feel for how WordPress works and how it all, works up together with administrators and junk like that, contributions. And then, maybe move Young Astronomers, and then finally the big site when we really know what we're doing. But that's kind of where I'm at with the website and the, moving that stuff out. And this is probably speaking for the communications committee as a whole. So
the option, the
Sorry.
company you're interested in is, what's the name of them?
HostGator. Sorry,
HostGator.
I unshared a little early, I guess.
Well, it was too small for me to read, so
Oh, I'm sorry.
it's not your fault.
Well, I
maybe
tried to put it
is.
up on the biggest monitor possible, figuring that might do the best, but yeah. Yeah, there's no good way of, yeah, it's hostgator.com.
I think the,
And this was 1165 was the monthly on that,
yeah,
compared to the other plans, which for the same services were around $15. So it was a little bit cheaper than the others and offered all the services and more. So it seemed like the way to go.
yeah,
Yeah,
I'm not arguing with your research. I'm sure you found a
Oh,
pretty
sure.
good deal there.
yeah,
But my, you know, the big policy question is getting off of the U of M server, because it is stable, it is forever. And what kind of, you know, track record does HostGator have, and how, what are their future prospects for, you know,
Yeah.
getting gobbled up by Elon Musk or whatever? And
Well,
and-
that's a good question for anybody, I think.
well,
Um,
he's unlikely to gobble up the university. That's,
Well, as far as like U of M stability, without anybody noticing, it's actually flowed through 3 different arms already. It's gone from ITS Central Services to ITS the whole, and now that service is actually being run by the medical school IT. And that's why we got a few more questions. I originally contacted my old college contact when I worked for the LSA to get to what the services was and whatnot, because he used to run the ITS service. And he says, no, we don't run that anymore. It's through the med school, and they've honored the past arrangement for free of charge, blah blah blah. And they've always asked for a short code in case anything has to happen. But with the medical school, because they're more cost and money aware than the university at large, they were not as convincing, as far as I could tell, of their intentions to keep it free, which that changes the equation. And they were talking to the tune of $500 a year, which I thought was a little
it's
steep.
exorbitant. Yeah.
Yeah. And it's like, that's the reason I went off and looked for these other services.
Okay.
Now, with that said, all these services I can verify, but most of them are going to use either Amazon, Microsoft Azure, or what's the other big Google, their cloud services. Even the university right now, they're running on Amazon servers. So
Okay.
we rarely run any of our own stuff anymore. So as far as that goes, all the
I
cloud
get it.
based services are kind of the same. It's just a matter of who's running the show. And at $500 a year, it was like, yeah, maybe we'll look around. And that's where this kind of led.
Okay.
Now, it's not guaranteed, but I certainly don't want Krishna's research account that our website is under. I don't want that to get dinged for $500 and have him try to explain what's going on. So it left me very uneasy the way they worded it.
Yeah, I'm beginning to understand now. So
Yeah. So if this is, remotely economical, I thought it might be a thing that we can at least try to. There's no reason we can't just say, no, it's not working out, cancel it, and we'll try the university. But this seemed to be a lot better way to go initially.
looks like a good bang for the buck.
Yeah. And it reduces some of our dependence on the university's goodwill too. So goodwill is one of those things you never know when it's going to run out. So.
That's right.
Yeah.
Any other questions on that? Well, I think I stopped sharing, right? Yeah. Okay.
Okay, is that it, Jeff?
I think that's all I got. I did, I can answer comments for our Emerson School thing when that comes up, but as Adrian and I ran the presentations there.
Great. Jim?
Jim, okay. We've had 3 member nights out at Peach Mountain. They went reasonably well. I sent an email to the officers outlining all the details. We opened at about 8:15 and closed down at around 2 a.m., more or less. A couple of those nights, Jack was out there running the McMath, and that was quite quite a bonus because we did have about half of the people that showed up over the 3 nights were new members. And so they got to see the McMath in action, and that was pretty great. The one problem is with the history of vandalism up there the past couple of years. The engineering school has put on the building up by the radio telescope an obnoxiously bright white floodlight to discourage evildoers, and it also is discouraging to try and observe with it beaming across the field. So Jack's been working on that, and hopefully we'll get it resolved so that we'll have the ability to turn it off when we're up there. The other thing is the COVID protocol. There haven't, I think our biggest night we might have had 7 individuals. So everybody had masks. Everybody had masks to go into the observatory. And I asked everyone if they had been vaccinated, though I didn't card them. If we run larger events, I think we would need to card people, like a public event, which would require quite a crew to do that. I think it's possible, but it's not possible with me and Jack trying to run a public event. We'd have to have at least a half a dozen lowbrows that knew that they'd have to come away from their scopes to help out. And so far, the response for the member nights, while I'm happy to seeing the people I did, hasn't been overwhelming. So I'm not sure how fired up the members are right now to be out on the hill. That said, the weather's getting warmer, or has gotten warmer, and possibly more nights on the weekend would help out. The first 2 nights were on weeknights. People had to go to work the next day. But even the one night that we had on the weekend did attract a horde of lowbrows. I may be out there tomorrow night. I'm keeping track of the weather, and it's looking possible. So I'll send out an email tomorrow afternoon if I'm going to be there. And that's the other thing. We're somewhat limited by the fact that you, Charlie, Jack, and I are the only ones with keys, and it kind of depends on when we're available. So far, that hasn't been a problem, but I can envision it being one. Like to hear from the membership at large as to how they feel about being out on Peach Mountain and what they would need to want to be out there or feel more comfortable being there. And I think that's it.
Thank you, Jim.
Let me ask, what are the prospects of getting that flood line turned off?
if Jack's still on, he's the one that's been
Yeah,
asking
he's here.
about it. So I think he'll talk to that when it's his turn to make a report.
Well, look, Jack's talking to him about it right now.
Yeah, we've also, some of us have been working on the 17.5-inch telescope, and as well as trying to solve problems with the McMath. The 17.5, we're concerned that the Sky Commander might not be working properly. We had it out under the stars a few nights ago, and at a certain point it lost its bearings. It no longer would knew where it was. And we had the scope apart. We had tested the encoders and all the connections and everything physical and electronic worked on the scope, but the Sky Commander let us down. So we're thinking we might have to replace that, but Sky Engineering is no longer in business, it seems. So the two alternatives we found are Astro Devices Nexus DSC Pro, which is an Australian company, and Argo Navis, another Australian company. And I talked to Eric Webster about the Argo Navis in relation to the McMath, because the Argo Navis on the McMath has been somewhat flaky, and he hasn't had any for a while. He's waiting on a shipment, and the dealers, US dealers for Nexus, one of them has a couple of units maybe, and the other one just doesn't. And the other dealers that they listed are telescope makers that I know have stopped making telescopes. So ordering one from Australia, we'd probably have the same luck as Eric would. The one thing about Argo Navis, even though they're more expensive, about twice as expensive, half again as expensive as the Nexus unit, is that Eric works on them. So if there's a problem with any unit we buy through him, he would be available to service it. And now I'm done.
Just out of curiosity, what does the Argo Navis cost? I have no idea.
If you get it through Eric, it's around $800, $700-800. You know, it's more of a concern for the McMath, because we're using it to take care of problems in the mount, as far, you know, as far as the mount being not quite at 42 odd degrees exactly, and in elevation and or declination rather, and other you know, quirks that the Argo Navis has the ability to make calculations to compensate for. That's not such a big deal with the 17.5, because the 17.5 changes every time you set it up. Because every one of these big telescopes has a certain amount of flexure in them that has to be compensated for, and other, you know, installation errors. But ones that change every time you set up the telescope, I don't know that the Argo Navis should be any more of service to us on the 17.5 than something we could get far less expensively, but Eric puts those on every telescope that he sells. That's the option he offers for digital setting circles, and there's a reason for that. They're pretty reliable.
Okay.
So Jim, I have a question or a comment. My experience, though, since my 16-inch is set up pretty identically to the way the 17.5 is, with Sky Commander and ServoCat and all that. What I've seen with my scope is if the scope sits for any length of time, and when I say length of time, I mean months, like over the winter, whatever, all those connections, so those wires, I don't know what they're called, but they're like an Ethernet type connector. Some of them are 6 conductor. I think some of them are 8 conductor. They seem to lose contact with at least 1 or 2 or more of the wires, and you have to take them apart, blow them out, somehow clean them out. It's kind of like the old Nintendo set. You had to take the card out and blow on it and all that baloney. I don't know if you've tried that or not before we conclude that the Sky Commander is going bad.
No, we haven't, and that's a good idea.
Yeah, I think you might want to do that.
That's one of the things that Eric suggested when I talked to him about the Argo Navis was cleaning up those connections.
Yeah, and how you actually get in there and clean them, but when they're exposed to the outside, there's moisture, and most of that stuff is probably, it should be gold plated and all that without corrosion kind of things, but for some reason they would, I had more problems with the connectors to the motors themselves, where a motor would stop working and then I'd have to clean that, but it's conceivable it's the connections to the Sky Commanders.
The connection in the rest of the scope has worked pretty well. When we push the button, stuff happens.
Not sparks, I hope.
Not sparks, no.
Yeah, okay, good.
Things you expect to happen. It just, it just doesn't go where we expect it to go.
Okay.
But if we are having, simple corrosion problems in the Sky Commander, what Eric suggested with the Argo Navis was to find connectors that you didn't want to use anymore, or old ones, and just shove them in and out a whole bunch of times until you cleaned up the connectors in the unit. So yeah, we give that a try.
Yeah, and I suspect it's not corrosion, it's probably dirt, or who knows, you could have a spider crawling in there, who knows, it could be anything.
Yeah, well, I guess that's possible, but we pulled the Sky Commander out and it sits in a case. It's not on the telescope unless we're using it.
Okay.
So,
well,
it's as
check it
well
out.
Protected as we can manage it. I suppose, quickly what our experience is that we don't quite get the accuracy that we want, and so we realign on object, and then eventually it loses its mind.
Yeah, I found that realign on object doesn't work very well, if at all.
Well, it would work, but if we stayed in that part of the sky, but
right.
So
okay. And we can take it offline. If you have questions, let me know.
Yeah.
Okay. Amy?
Yeah, hi. I don't have a lot. Just want to thank everybody for all the contributions so far. And there's one question I have is, now that events are sort of starting to come back, I'm wondering if I'm supposed to be actively soliciting people to write up a review of, or a report of an event, or if this is something that I can just expect people involved will submit, because I've not been the newsletter editor during any period of time when we've had events, believe it or not. So just wondering how that all tends to go.
In the past, any reporting we've done have been officer reports at meetings about how the open houses went the previous month or the member nights. There have been reports on observing events we've done at places like the Yankee Air Museum, for example.
Yeah.
Well,
like the
and
Emerson
other
event.
venues.
Wasn't there just an event at Emerson?
Yeah.
So,
Yeah.
and I can assume somebody will probably submit something for the next newsletter, or
Yeah, we've even got pictures, so.
great. Okay. Just
Maybe I
wondering.
imagined it, but I thought I heard somebody say that they were gonna write up something on that.
Yeah, I think Jeff made a noise, but
Oh, great.
his
Okay.
eyes just got real big.
Well, if we didn't hear it, we heard it now, right? Yeah.
Does seem that way, doesn't it? That's
All
fine.
right.
I can write it up.
But that's it, Charlie. That's all I have.
Okay,
What's your
thank you, Amy.
deadline, Amy?
Well, it's always the 7th. I'm sorry, the first of the month, because it comes
Oh.
out on the 7th.
Okay. I can get something to you from Emerson from there.
Great. Thank
Appreciate
you.
it, Jeff.
No problem.
And great job again, Amy. Okay, Jack.
Okay, we'll start off with a few things. There's some questions I know people have. On our membership nights, we're out at the observatory. Jim talked about the security light switch. I did do a test with Professor Cutler Wednesday. I was out there doing some work at the observatory. We did it by text messaging and that. And he is shutting the light off manually through some kind of electric Wi-Fi messaging system or something that they have set up out there. And the only thing I've got with it is I have to text him to shut the light off, text him to turn the light back on. So we have to text him at 2:30 in the morning to turn the light back on. And I'm trying. So the discussion was in the email I wrote him about, let's just see if we can come out with a time or a time limiter of something and use some kind of timer on this Wi-Fi system. So we just say, okay, we shut it off at 8:30, turn it back on at 2:30 a.m. in the morning. And I don't have to chase him around. So I'm waiting for an answer on that. But they are working on it. And there were 2 lights shining out. One of those lights was taken off and unscrewed, and the light shining towards the dish is the one that's on. So some of that light has been cut down already. The other thing is with the fire extinguisher. Our representative from the Environmental Health and Safety for U of M was out there, fire inspector, and they looked at the extinguisher, said it was the right type, and everything checked out okay. They just tag and check them yearly, but according to our representative from the Facilities Management Office, Amanda Keel, everything should be okay. So fire extinguisher, and that's okay. Other issue was the cutting the lawn. I was out there Wednesday, like I said. Lawn out there by the observatory has not been cut. I did send Susla Fernandez a letter just requesting that we would like it cut because we're going back to the members only nights, things like that. And we do have a special program going on August 1st with U of M Math and Science Group. So I'm waiting for an answer on that, if they're going to have a specific time date on that. The other thing that Jim talked about, and yes, we're having some problems with the 17.5 inch, and we need to do some more testing. I did a little testing on the arm that we have on the altitude encoders and that. if we have to kind of do some work on that arm, it's a little too loose. If you move that arm around a little bit, you will see the numbers change on the Sky Commander. But that's something we can take care of and do. The issue Jim talked about was much more important. And the idea of going in and cleaning out the encoders and that is a good idea. There might be some other things we can do too, because it did sit there for a couple of years when it wasn't used. Matter of fact, I don't know if this makes sense, but you know, they have this air spray you buy for cleaning out keyboard keys and stuff. You spray it in there and it blows out all the dust in that. I don't know, maybe doing something like that where you plug in the encoders and things, spraying that out with that air might
Contact
help.
cleaner.
I don't know, but I'm just thinking of that because I've used it on some of my electronic stuff at home and that. So that's another idea we can try and do. But yeah, we can get together and do some work out there.
It would be better to use the contact cleaner than just air. Because if it's been sitting around for a couple years, there's stuff that could have built up on it.
True. I'm trying to figure a way to get it in there. You could probably use something, wipe it on a little, I don't know, ear or something. And
There are aerosol ones that have the just like WD-40 have the straw sticking out.
Oh,
Yeah,
okay.
Jack, if you want to do that sometime, get in touch with me. I can bring out some, high quality industrial contact cleaner. Really, all you need to do is spray it into the contacts. It evaporates very rapidly, and it has high penetrating quality. So maybe we can get stuff working there. Get in touch.
Yeah, we'll put that together. I'll get back with Jim and whoever else wants to get involved in that, and then we can go out there and test all that.
And the other thing I would ask, Jack, is can we take a mower out there and cut the grass around the observatory and on the lawn if it's necessary? If we think it's
we may end up doing that. We could probably, somebody could bring in their lawnmower.
I can bring in my garden tractor and cut that pretty quickly. It's not a problem as long as it's not a problem with the university.
Yeah, that's what I'm waiting for Sushil to get back with me to see what the decision is, and we'll take it from there. But yeah, I did tell her though that we do need it because we do have some U of M events coming out there. So I'm hoping that would, will help speed up things, or at least set up a date and a time to get some of that caught. Yeah, it's very true. Okay.
Well,
All right,
Jack,
thank you, Jack.
do you need a new fire extinguisher out there?
No, I asked them that question. They said no.
It just has to be
Everything's
charged?
okay. Pardon?
It has to be charged, is that it?
They said everything was okay so far.
Okay,
The
all right,
inspector went out there because years ago, I did take it back in to a fire department or something. And they said, yeah, everything's fine. And this guy is in charge of doing this for the university.
okay,
And they said, it's okay. They just want to tag it and verify it every year. And I said, fine. If you can't get in there, let me know. I'll come out and do it, but I guess he's got a key. I have
Probably
a situation here. So
Okay.
I'm going to log off for right now for a couple minutes, okay?
okay.
Okay, Doug.
All right, well, I've got some interesting news. Since our last meeting, we picked up 7 memberships in 1 month. I don't think we've ever done that. It's for some reason,
Great.
since we're not having events, we're getting more and more members. So we're up to 175 dues paying members. And then if you add the 14 that we've been carrying because of COVID, we would have, without that, we would have dropped them by now, but that puts us at 189. So it's pretty amazing. And we're at the same time they're paying dues and all that. So we're up to $13,463.02 in our treasury now. $352.50 is going to be sent in, or thereabouts is going to be sent to the Astronomical League, because that's money I've been collecting for that. And let's see, since our last meeting, paid $9 to send a cap to Rudy Lidner, our May speaker, and then our usual paying for printing and mailing the newsletter for those that subscribe. I think there's only 9 people that do that. And then our AT&T hotline, that's been the same price, $15.85 a month for as long as I can remember. So those are just our usual expenses. Let's see, what else did I do? I filed our annual e-postcard, which is basically we're a 501c7 social club in the ICPI of the IRS, and we have to file a little electronic thing once a year to say that we're still in business and our annual receipts are under $50,000. So I did that, and then before the end of the month, I need to send a size large t-shirt to Dr. Z, and also finish collecting any money for Astronomical League that people might still be wanting to send. I have to send that in before the end of the month. And I've got about half of the members, or let me back up. Most of you may know this, but one of our members graciously sent us $75 to use as, not 75, whatever 750 times 6 is, enough money to give Astronomical League gifts to 6 members. And I think we've already settled on some of those that showed up at the members only night, some new members that don't necessarily have Astronomical League, and then I'll have to come up with another 3. So I'm open to suggestions on others, but I'll probably pick from some of the latest memberships that have come in over the past year or so and see who looked enthusiastic, and maybe they didn't show up at the members only nights, but I'll come up with 6 to include with the rest. So I think that's everything I've done in the past month.
Kind of thinking, Doug, with that amount of money in the treasury, we got to think of something to buy. One thing we
Down
could
payment?
consider, we were talking about buying, I think it was called a Raska telescope or something. Norb Vance talked to us about it. It's one I think you hook a camera up to and you can project an image with it. We were talking about maybe as an addition to for the McMath, for open house events. And I think Norb has one of these over at EMU, so maybe we'll get a chance to see it next month. And if we like it and everything, it might be something that might be a worthwhile investment. So
yeah, I mean, it depends. We when we raised our dues a few years ago, it was maintenance on the McMath and all those things, and we really haven't been spending much on much of anything. So the one thing does come to mind looking at John with the GLAC and astronomy at the beach. Have we settled on a suggested donation for us to donate towards that? John Wellbank?
I'm kind of waiting for a response from the officers. I haven't heard anything.
Okay. Well, what do you have a suggested?
We are, yeah, and I apologize for this.
I don't remember.
Yeah,
in the past, the records show that was around $400.
Yeah, it was $400.
Okay.
Most times. We didn't send anything last year. And we might not have the past 2 years, but just say the word and I'll write the check.
well, the last 2 years, Doug, we haven't had
Expenses.
marginal expenses. We had to pay some bandwidth and such, but this year we have actual expenses, and so yes, Adrian Bradley is the treasurer of GLAC, and he has the account information. I'll have Adrian get in touch with you about that.
Well, I'd like to move that we spend $400 donated, whatever your expenses are, unless you think or he thinks that that's way too much, but
not too
seems
much.
like Sounds like that's a good round number. We could even bump it up a little bit considering the state of our treasury. So
And we could call it a nice 500.
we could move it up to 500.
I support that.
I
I
agree.
There we
move we
go.
send them $500.
Okay. I'll do that.
I don't hear any
Contact,
objection.
Adrian.
Yeah, we should vote on it before you write the check.
Well, I don't have it right in front of me, so you might even take PayPal. I don't know.
I don't know if they
Since
have,
not all the officers are here, I'll just send an email tonight or tomorrow and get a vote from the officers. I think it's
Well,
pretty
then
safe to
we
say
got
that
the
it'll go
members
through.
here, so we can just ask them.
Well, we do have a majority here, and I don't hear any objections, so
Yeah, but
good
it is,
point.
yeah, no, but this is beyond our remit, I think. We
It
have to
is.
ask the members if they want to.
That's a good point.
Oh.
Well, I think
Oh.
we made an exception with black though, remember?
Did we?
Yeah, and if
I
it's
guess I don't
exact
recall.
$500, I think that's an exception too. No, I'm just kidding.
Right.
But we can move the question right now and ask people what they
Okay.
think.
Let's do it. We have a motion and support. Discussion, anybody opposed?
Favor of it?
go
All in
for it.
favor?
I,
Aye.
I,
Anybody opposed? There we go.
So moved. So, okay.
Thank you very
Cool.
much.
Thank you.
That's a big help for GLAC.
Okay, now I'm done.
Okay. I don't see any other officers. I thought I saw Brian for a moment, but I don't see him now. So does anybody have anything else? Okay, hearing nothing. Do I hear a motion to adjourn?
So moved.
Okay.
Support.
Is anybody opposed? Okay, thank you very much, everybody. Have a good rest of the evening.
All right. Take care, everyone.
Hopefully we'll
Yep,
see you
good
out at
night, all.
Beach Mountain. Take care.
Yeah, hopefully tomorrow night.
Yep.